I am small, so I have to lower the mic. Okay. Dear KPS members, it's my great honor and pleasure to welcome you all to this ceremony of 2025 Benjamin Lee Professorship. The KPS has organized this special event and lecture series in the close collaboration with the APCTP since 2017. This is in keeping with our KPS tradition to recognize and celebrate excellency. Using this opportunity, I want to congratulate the 14th recipient of Benjamin Lee Professorship, Professor Peter Zoller at the University of Innsbruck and IQOQI, Austrian Academy of Sciences. I also hope that this event will be continued to future opportunity for our young KPS members to interact with the world-leading physicists. Thank you very much for your attention.
Thank you very much, Professor Jinhee Yoon. Now I introduce the President of APCTP, Professor Misao Sasaki. He will shortly introduce the Benjamin Lee Professorship. Please welcome Professor Sasaki.
Good morning. I'm Misao Sasaki, the President of the APCTP. As you can see from this slide, Professor Benjamin Lee was the foremost Korean theoretical physicist. His work paved the road for the standard model in elementary particle physics, which is the culmination of fundamental physics in the 20th century. The Benjamin Lee Professorship Award was established to commemorate and continue his legacy. Maybe just my small personal experience when I was a graduate student, he published this very kind of legacy physics report review on gauge theories, and that review was really a Bible for us. So I really am happy to introduce Benjamin Lee Professorship Award. Thank you.
So since 2012, we have been selecting the most distinguished theoretical physicists in the world as the award recipient, as you see in the slide. So I am very happy to announce that Professor Peter Zoller is the recipient of the Benjamin Lee Professorship Award in 2025. So today, we are very happy to announce that the 14th Benjamin Lee Professorship will be conferred on Professor Peter Zoller at the University of Innsbruck and also Australia and IQOQI, Austria Academy of Sciences. So now please welcome Professor Zoller. So, Professor Peter Zoller was selected as the 14th recipient of the Benjamin Lee Professorship for his significant contributions to our understanding of the physics of quantum simulation, quantum information processing, and quantum sensing, which have profoundly advanced the field of modern quantum science. October 22, 2025, APCTP. Okay, please give him a big round of applause. So now we would like to hear the acceptance speech from the audience.
It is a great honor to receive the 14th Benjamin Lee Professorship. I would like to express my sincere gratitude to the Asian Pacific Center for Theoretical Physics, the selection committees, and my colleagues and collaborators who have been part of this journey. This award is not only a recognition of my work, but also of the collective effort of the quantum science community. I feel deeply humbled and inspired to continue exploring the frontiers of quantum science, and I thank you very much.
Now we take a commemorative photo with Professor ZOLLER and the President of KPS and the President of APCTP. Please welcome all of them. Okay, this is the end of the award ceremony, and we now begin the plenary talk. So from now on, the plenary talk will be chaired by Professor Sung Lee of Costa. Okay, thank you.
Thank you. Let's get started the plenary talk with the title Simulation with Atoms and Ions. It provides us the progress and the future of quantum simulator toward quantum advantage. Let's welcome the speaker.
Let me thank you very much. I mean, it is a great honor to receive this professorship here, and I've been traveling now around in Korea, for the last 10 days, and I'm quite amazed about, the quantum science which is happening here. And I would like to tell you today a little bit about, quantum science and technology, but I should maybe start out by recognizing here that, as has been said now several times, we are celebrating this year 100 years of quantum mechanics. It was, Heisenberg and Schrödinger that formulated quantum mechanics in the way that we understand it now. But it is also time to recognize some important, scientists that contributed. And last weekend, Xian Yang passed away, who was actually he was the founding president of the Asia Pacific Center for Theoretical Physics. And I think that he was a great and fantastic scientist, an example of how to do theoretical quantum physics, and I will come back to some of his contribution, at least indirectly, by talking a few words about quantum simulation of lattice gauge theories a little bit later on in my talk. But we're not only celebrating 100 years of quantum mechanics. I belong to this quantum science and quantum technology community. We're also celebrating, I would sort of say, 30 years of quantum information. I somewhat arbitrarily define here the birth date as the invention of the famous Shor algorithm that sort of made people aware that building a quantum computer and quantum machines would be beneficial, allowing us to solve problems beyond what we can do classically, and this is really my talk for today. So I will speak about quantum information, and in particular then about how to realize or how to implement quantum information ideas from quantum computing to simulation using AMO. AMO stands for Atomic, Molecular, and Optical Physics. I'm one of these people, I'm a theorist, but I'm one of these people very much interested in having atoms interact with laser light, atoms being controlled by laser light, and atoms and molecules and also photons eventually sort of playing the role of the basic constituents, how we build quantum computers like big qubits and so on. So atomic, molecular and optical physics is one of the best ways actually of implementing quantum information processing. And the history goes back basically also now 30 years, and it was a long journey. And what I would like to do in my talk is to tell you a little bit of physics, and at the end then come to topics that we're working on at the moment. So I'd like to give you, an insight what we're interested in right now. But I guess I should start with some history, and then at the end also give some outlook, how I see the field developing in the near future, maybe then also a longer future on this quite interesting endeavor here. So if you allow me to sort of draw a timeline over here and ask, what are the birth dates of quantum computing or quantum simulation, I think that Richard Feynman, known as a Nobel Prize winner, in the context of high energy physics, particle physics, quantum electrodynamics, and but he was a very universal, figure in this whole context, and he had this vision of building a quantum simulator, and this was in 1982. And if you go back to these days, he wrote a couple of publications that are very general but sort of very visionary. He came to the conclusion that a classical computer can never efficiently simulate a quantum system. And it is, there's this famous sentence by him, nature is not classical, damn it, and if you would like to make a simulation of nature, you'd better make it quantum mechanically. And this is the idea that quantum computers, quantum simulators, are sort of a better way to model nature in the sense of nature being quantum mechanical. And of course, all of these things have to do with the fact of the recognition that the fundamental feature of quantum mechanics is, of course, entanglement. Entanglement in the sense that if I got a many-body system, I'm drawing here some magnetic system with little spins, they can be up and down, that a quantum mechanical state of a many-body system is actually a superposition, in the sense of Schrödinger's superposition state of many of all of these configurations. Of course, the emphasis being that there's an exponential number of them, and you can see that when you see the exponential over here, and that is the number of particles. There's many, many terms over here. If you would like to represent this classically, it's essentially impossible except for very, very small systems, but quantum mechanically, a quantum mechanical system, to the extent that you can control it, can actually do that. But I mentioned before that, when it comes to quantum computing, maybe the right birthday would be 1994 or then also 1995. And this is here Peter Shor. He was the first one to show, in the context of a particular algorithm here, that a quantum computer can solve classically hard, but also relevant, that's important, it's not a toy problem or whatever, relevant problems outside of physics. And 1 year later, he was the one who wrote the first publication about quantum error correction, pointing out that a quantum computer can be built from imperfect components. And I think that this is conceptually very important. First, that it has a relevant thing, but also that we can build physical devices that might be imperfect, but using quantum error correction we can make them perfect, leading to this notion of actually fault-tolerant quantum computing. At the same time, of course, the question came up, how to build a quantum computer. And today we have several answers. With Ignacio Cirac, who is over here, was my postdoc at that time. We came up with the idea of the trapped ion quantum computer, and I have a few slides trying to tell you qualitatively what these ideas were. The question how to build a quantum computer with AMO, and it turned out that atomic physics was particularly well set up to answer these kind of challenges that appear in this context here. But just after the Shor algorithm motivated all of these things. But of course now we have several other things. We have neutral atom computing with Rydbergs, we have photonic quantum computers, we have superconducting that I'm also listing here. These are artificial atoms, not the natural atoms that we are using, so strictly not part of AMO, but we have them as honorary members in our community. And let me add to quantum computing also here quantum simulation, all of these ideas of analog quantum simulation. So this here triggered then a whole series of theoretical papers. But the interesting part is that many of these things, initially being theoretical idea, made it into quantum devices today that exist in labs and come back to them, that we can play with them and use them in a way that we can make the original vision sort of a quantum advantage that we have more true. And then if you allow me to go back sort of as a historical note over here, I would like to give here credit to Arthur Eckert. He was the one from Oxford in the proceedings in a conference held in Boulder, it was in 1994, that came to the atomic physics community, and he said, well, Peter Shor just published a paper over here pointing out that if you can build a quantum computer then, okay, and then the whole story goes. And he used the podium of this conference over here in Boulder. You see here Nobel Prize winners Carl Wyman, Dave Wineland over here, to address the atomic physics community, asking, does the AMO community know how to build a quantum computer? And he explained to us at that point, what the quantum computer really means in the context. We call this the quantum logic network model, that we had a set of qubits over here, two-level atoms, spin one-half systems, which we can manipulate by, for example, what we call single qubit gate, just operating one of the qubits or maybe entangle them in a certain way, and then build up whole circuits, and then doing it this way, a quantum computation by itself. There was this notion of qubits, quantum bits, put them together into quantum register, quantum gates. There's preparation of initial states, then readout at the end, and of course very important, no decoherence, isolation, the whole system. And the main challenge, of course, was how would you take a real physical system and do all of these things, but in particular there was a question of controlling entanglement. Do we know how to make controlled entanglement in an engineered many-body system, which is a quantum computer? And Ignacio Zirac and I sort of had an answer because we were working on a problem that was basically the answer. We just didn't know that the quantum computer was sort of the real application or the real challenge to build. And this was based on the fact that during this time in Boulder, I had a lot of interaction with Dave Wineland, who was one of the clock builders. Trapped ions were developed originally in the lab for being very good atomic clocks. And atomic clocks have evolved over all of these years to incredible precision instrument. Today, atomic clocks can operate on the level of 10 to the minus 20, 18, 20 or something like that. And this was the way of going there. And I think that's a very good starting point if you would like to build a quantum computer. This kind of an engineering precision and the underlying ideas were very much matched to these things over here. And the experimental apparatus behind in these labs was the linear ion trap. You can see here individual ions, these are stored, they're trapped, they are charged, they repel each other, they have a certain motion, that you can cool down with the laser to very low temperatures. And now you can see that the qubits from over here correspond to an electron in the atoms over here having either spin up or spin down. So these are individual qubits that you can see over here, and we would like to match this physical device over here to this. And the question, of course, was, how do we get entangling gates? Well, it comes here from the fact that these ions can also move. They can move if you cool them down to 0 temperature, a superposition of different phonone modes. And this collective motion over here basically leads to a model like this, that you have your qubits that are coupled to phonones and are like a kind of a collective mode or quantum data bus. So this is a quantum data bus where qubits can talk to each other, and we can use laser light to switch these things on and off. And this was sort of the underlying model. I'm not going to enter details over here. But the basic idea behind all of that was that actually very soon implemented. This was our theory paper now 30 years ago, pointing out these ideas. And then very soon there was experimental demonstration. This led to companies today. And if you look at the fidelities, what the quality is of the gates that this community does at the moment, you see a lot of lines over here. This is from Continuum, but there's other companies now building these things. And of course, this is ongoing research in the lab. In particular, also, of course, in the context of research that's going on here in Korea. We have here the conflicting requirements, that we would like to control a large many-body system. We would like to scale it up. We would like to avoid decoherence, and these sort of conflicting requirements are the ones that are the big challenge that we are tackling right now when this whole problem sort of moves from basic science more and more to becoming an engineering problem. In the meantime, of course, when I talk about ions over here, there's ways of getting many more ions. I'll show here data from Luming-Duan, with 512 ions. Innsbruck has very similar results over here. This would be a 2D ion crystal doing quantum computing eventually, and of course acknowledging the effort which is going on here. I don't want to say much more here about ions, but rather switch over to another platform, where we also made our contributions, which is neutral atom quantum computing, which at the moment is also, I would say, one of the most promising ways of doing eventually fault-tolerant quantum computing. And again, let me show you what the original ideas were and how they are now implemented in today's work. I should sort of mention on the side that 1995, over here was an exciting year, also because of a different reason. Because in Boulder, when I was there as a professor at Chile, University of Colorado, the first Bose-Einstein condensation was created by these people over here that eventually received the Nobel Prize for doing that. It was essentially cooling weakly interacting gas, down to basically zero temperature, where if they are bosons, they condense. You can see the Bose-Einstein condensation over here. These are famous pictures that you find everywhere, similar development with the Fermi gases. So these developments provided us with very, very cold atoms, where the motional degree is completely controlled. And of course, that's a good starting point now also to think, can we use these ideas or these underlying experimental results here to build a quantum computer. I would say that most of the work that I personally did during this line was much more to go from neutral atom quantum computing to analog quantum simulation. And I say a few words about quantum simulation then actually later on. Let me just mention here that this led then to these ideas of using laser-excited Rydberg atoms in tweeze arrays, and let me outline just briefly what the underlying ideas here are. I guess all of you know tweezers in the context of manipulating cells in biological systems, where you take a light, you focus it down to a very small focus, and then use that in order to drag, biomaterials around, cells around. We can do the same thing with an atom. We can focus laser light, and we can try to catch single atoms, and these tweezers being independent of each other, we can arrange these atoms in any configuration that we want. And the question is now, well, we got an atom here, 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 we can build two-dimensional arrays, even three-dimensional arrays of these atoms. How can we build now a quantum computer using that? The question is, how would we entangle it? We can easily do single qubit rotation by just taking laser light and shining on one of these ions, but to get entanglement was sort of the open challenge in this case. So it is now, I guess, about 25 years ago that we came up with ideas. We had work ongoing in Innsbruck, where we wrote this paper, Fast Quantum Gates for Neutral Atoms. And while writing our paper, with Dieter Jaksch, Ignacio Cirac, we discovered that Misha Lukin had sort of related ideas that led eventually to this thing over here. Said, so why not collaborate? I think that this collaborative spirit is very important in this community. Let's do this FastGate together, and then we also do this thing over here together, where we worked with atomic ensembles. But let me point out now, and Misha Lukin, of course, is now one of the key players on the experimental side. At that point, he was still a theorist, as you can see over here. So what was the underlying idea of entangling atoms, that are maybe 10 micrometers apart from each other? You want this to be a basic gate that we have in quantum computing. It is something that we call the Rydberg dipole blockade mechanism. And I think it's actually very easily explained sort of by hands. If you got two atoms and you excite one of these atoms up to a Rydberg state, put it very high. If you would like to excite the second atom also in addition to the first one, there will be, it turns out, these are Rydberg states, they are huge. They're as big as a small virus, when you excite them to these highlight Rydberg states that have an n quantum number of about, 60 or something like that. They are really huge atoms, they're very polarizable. And if you do that, they will interact very strongly. So if I excite one to the Rydberg state and I would like to excite the second one, they interact very strongly, so it means I have to provide more energy, but the laser doesn't provide this energy, so I can excite either one, I can excite the other one, but I can never excite two at the same time. And this is what we call a Rydberg dipole blockade mechanism. Those of you that are familiar with quantum dots, you know, we have the so-called Coulomb blockade, that you can only put one electron into a quantum dot, and there's a sort of a similar mechanism over here. And I could go through the properties of all of that. I mean, it has amazing properties, and today I would say it's kind of the transistor, unquote, you know, that underlies all of this neutral atom computing. There's a similar way if you do atomic ensemble, if a few atoms over here, the fact that you can excite only one of them, this leads to this notion of the super atoms and making very strong nonlinearities and so on. This was the underlying physics, you know, that we sort of outlined there. Here's the mechanism, you know, of exciting too, that you also don't have any forces in this context, but maybe this is too technical, I'll skip it over here. So first experiments along these lines were done then. Well, it was the 2008-9, you know, in this time. And they were a little bit disappointing because the gate fidelities were only 85%. But it was the first experiments, and these are the two gentlemen over here that deserves the credit for doing the first Rydberg gates, you know, along these lines. In the meantime, you know, if I see the progress, this was published just now, not too long ago, we see now entangling gate fidelities that again have 99.9. So this is a mechanism that works. It is scalable to a very large number of particles, and it underlies, for example, of these very recent publications by the group of these gentlemen over here, Misha Lukin, Markus Greiner, Vlada Buletić, that build now large-scale logical quantum processors based on reconfigurable atom arrays, leading basically to fault-tolerant quantum computing. They could show that they could implement error correction, and this is sort of the status today. And I think that we've gone a very long way from these basic ideas, you know, of how to do these kind of gates to this kind of computing that we do right now. And I have here one slide that I borrowed from Misha Lukin. You know, this is this reconfigurable array. You can see the individual atoms over here. You can move them around at will. You move them together, you can perform a gate, you know, then you move them apart, you shine laser to make sticky qubit operations. And here's an idea of moving them around to be published actually a long time ago, but with ions. But today these things are now done with atoms, and this is a movie, you know, from Harvard that shows how atoms are moved around individually and actually in actually parallel over here, doing gate operations and doing some computation that you have in mind. I would say that this is, at the moment, is one of the best scalable way that is able to go to very large particle numbers. And the most amazing thing is that this community has now all shown, for example, quantum error correction, you know, what I talked about before at the very beginning. Of course, there would be more to say about quantum error correction, but let me sort of skip these things over here and come to research that we are doing actually right now. So I give you a little bit of history. Let me now tell you where are we at the moment. And I want to give you now examples of papers that we have published recently, and to continue with this neutral atom work. Let me tell you a little bit about research that we as theoretical physicists have done together with QEA, which is the company, the offspring of Harvard, MIT, building a large-scale tweezer array. And the particular machine that we'll talk about now, this exists in the company, and we've been using it together with the experimentalist here, is a 256 qubit machine. But we're not going to run this thing now as a quantum computer. You can do gates and all of that. What we wanted to do is more in the spirit of Feynman, the original one. We wanted to run it as a programmable analog simulator, and I will have a few slides trying to explain to you, but also the underlying physics problem that we were trying to solve. Basically, what an analog simulator does is this, that you start out with a question, well, I got a certain many-body Hamiltonian over here. You know, there's some single Pauli operators over here connecting, you know, for atom number L, you apply laser light here. Then you got interactions over here, like the dipole blockade mechanism that you have. So these things, if you shine lasers continuously to induce this excitation of the Rydberg state, they realize sort of these Hamiltonians here, and we are not going to enter the details of discussing here what they mean now physically. Basically, what you do in an analog simulator is this, that you sort of create synthetic quantum matter with a neutral atom array, and you can dial in many different, many-body Hamiltonians over here that realize different form of many-body interactions. In some sense, you know, you build an analog device of a many-body system in a very controlled way, with a lot of control knobs, given by lasers and a way of reading them out individually that you cannot do in the normal condensed matter systems because they're much smaller. Here the distance between these atoms is on the scale of 3 micrometer, maybe 10 micrometer or something like this, so we can resolve all of these things with optics. We can take pictures, single shot pictures of all of these different speed configurations, sort of having an eye on this entanglement and these complicated many body states that we can create. So the particular example, and I'm going back now, of course, to famous people that are doing quantum field theory and high energy physics. Let's talk about an example which is lattice gauge theory and illustrated by the very illustrative example of string breaking in a 2+1 dimensional Rydberg simulator. So I will show you now some theoretical concepts and then how they eventually emerge, in a device that we have over here. I should mention here that there were 2 publications. You can see that this is in June, so we are now this year. 2 publications parallel. One was from Google. They did a digital quantum device, a quantum computer, simulated some of these things. We did the counterpart using cold atoms and analog simulator. And both cases it was sort of similar physics question. So I will tell you now the following about this observation of string breaking in a 2+1 means time, so that's 2 spatial dimension, 1 time dimension over here, Rydberg quantum simulators. And credit should go, of course, to these people. Daniel was a postdoc in my group, and also Thorsten, and the other ones are mainly experimentalists over here from the company Quera, and Michel Lukin is here, of course, representing Harvard in this 2-dimensional array that we have. So what is the physics, sort of, that we would like to see, that we want to program now on this quantum machine and see if it is there, and it is to some extent a highly non-trivial physics. Let me try to explain it to you sort of by hands, and then you will see what the experimental results would be. So all of you know that if I take 2 charges, like over here, there's a plus charge and there's a minus charge. Of course, classically you will have an electric field line connecting them. It is also clear to you, this is like a capacitor. If I pull this thing apart more and more and more, you're storing more and more energy, electric energy, into this field line that you have over here. But in quantum electrodynamics, what can happen is this, that if you put in more and more energy, at one point it can be advantageous to create from the vacuum electron-positron pairs, because if I create an electron-positron pair from the vacuum, the amount of energy that I need for doing that would be 2 times the mass of the electron and the positron. Then you can break up the string, like the string that you have down here, because then you will be sort of screening off this charge over here, screening it off over here, and you can see this potential for 2 charges if you pull them apart. And there's very, very similar things also in quantum chromodynamics. You pull over here, it gets more and more energy, but at one point the string will be broken here, and we wanted to see this as real-time dynamics, something that people in this community, if you're high energy theorists that you would like to calculate string breaking in quantum chromodynamics, is a problem where we don't really have the technical tools for doing so, but quantum computers can actually do that. So why simulate lattice gauge theories? Well, I just gave you the example that we have things like quantum chromodynamics, we have phase diagrams in equilibrium at high densities. We don't know how to simulate these things here, and there will be processes, and so real-time dynamics and finite baryon densities are examples where we see that quantum computers, these quantum simulators could sort of fill in the niche, because we are lacking classical computation techniques to compute these things. And of course, this whole thing also carries over with the need to condensed matter physics. So there's motivation. And of course, what we do in the context here is just a very, very simple toy problem. But I think it serves as a demonstration of what these quantum machines can actually do today. And they do actually allow us to simulate things, certain phenomena, more as toy problems over here that, are sort of indicating that maybe in the future we're able to do then really interesting calculations along these lines, give the system time to develop. So if I just want to show you some results, I said before, here's your Rydberg 3 arrays, here's all of the atoms, you address them individually with laser light, and here's some Hamiltonian that contains the lasers that we are shining on the atoms, and the atoms will interact in a certain way. We have here, for example, the van der Waals interactions. If 2 atoms are in the Rydberg state, there will be a 1 over to the power 6 interaction. the coefficient C6 is scaling like n, the principal quantum number of the atom, to the 11th power. So this can be a huge number that we have over here. And you get that the Rydberg blockade, as I said before, made either one is excited or the other one, but never both at the same time. So this is the kind of model that I realized at the lab. For those of you that are experts in lattice gauge theories, let me point out that this blockade, the Rydberg blockade, can be mapped over to a Gauss law, which is these symmetries that we have in lattice gauge theories. But let me not enter here these technical details. What we have then is this, that you can create, in your experimental device, any configuration that you want. You can see that this is a Kagome lattice over here, and we put individual atoms here. And these atoms, when you drive them with the laser light, can be either in the ground state or they can be in the excited state. And you can see that atoms at a certain distance, like this one in the Rydberg state over here, this blockade mechanism ensures that all of these atoms within the circle that we have over here have to be in the ground state. So there are certain allowed configurations in this very high-dimensional Hilbert space that we have over here. And we can actually map, and this is again technicalities, and I'm not going to explain this in detail, these kind of configuration to the picture that I had before of charges and then, field lines connecting this, sort of being flux lines of gauge fields that we have in our lattice gauge theory. So you go to the machine, okay, and when you take a two-dimensional system, you can see there will be different string configurations classically. Before I talked about, superposition states, and we talked about, different spin configuration. Now it is sort of, a configuration where we have a broken string, these are the charges over here, and here is our string lines that we have. And quantum mechanically, in a device like this, you have a superposition of all of these things at the same time. If you do a phase diagram here, where you have the string tension, how much tension you need in order to pull the string, or what the mass of the particle is, which in our model is mapped onto some laser parameters, you can identify certain regions where you would expect that the ground state is a string, the one over here, or you can go to a certain region of, for example, very strong string tension, where you get a broken string like the one over here. And what the experiment now trying to demonstrate is this, that if you go to the region where we have actually here strings, so one of these realizations over here, and we can measure them because we got our quantum gas microscope and can see all of these configurations, as real pictures in the machine. You can see the probabilities for finding 1 to 6 over here is these configurations here, and you got 0 for that. But if you go to another region over here, where we expect theoretically a broken string, indeed, this is the broken string configuration as the dominant one, and all of the other ones are 0. I could show you a lot more results and explain them in detail, also for dynamics, for these things, but I think you sort of got the point of my story here, that these devices that we have right now are amazing, in the sense that there's control which is now available here in the systems, and does highly non-trivial simulations. But let me switch over now to something that I think is very important for future discussion, and discuss here a little bit something that we call inverse quantum simulation. I think the big challenge that we are facing in this quantum science and technology is that we would like to find applications of quantum machines, here for example quantum simulator, that demonstrate what we call utility. So something that is sort of, that we are doing something useful. And I would like to illustrate to you now some ideas that sort of this utility of trying to do something useful with these machines that we might not be able to do classically, like using this quantum advantage and machine learning over here, where all of these things are coming together. This is theoretical ideas I will tell you now, but I'm sure that they will make it into the lab actually quite soon, and they're sort of trying to think ahead. Can we do something which is very useful, and then we do something that sort of could inspire future developments? I've called it here quantum material design, knowing that many of you are maybe experts in real quantum material design. Note that I put it under the quote over here. So these are thoughts of how to design quantum materials in an algorithmic way. We are doing toy problems still at the moment, where we say that we would like to design quantum materials like superconductivity and so on with desired properties that you write down using programmable quantum simulators as a tool. And we're just doing now concept and toy problems. Maybe at one point this will advance to something of really being of practical use. At the moment this is an academic demonstration where we just talk about theory. So what's the idea? Well, the idea is actually like this. When we normally talk about quantum simulation, we do the following. We have maybe a quantum material. We write down the Hamiltonian over here. We go to our quantum simulator device and we, well, study interesting things. This could be some equilibrium phenomena, phase diagrams, for example, maybe some non-equilibrium phenomena down here. This is what the standard scenario is, and I've just shown an example along these lines. So it is along the lines of solving a microscopic problem, a microscopic description, writing down the Hamiltonian, solving on the quantum machine the many-body problem, and then studying emergent properties like, for example, phase diagrams. This is what I've just shown you in the example of the spring breaker. But you could also do the inverse problem. Inverse problem in the following: suppose that somebody has prepared for you on the quantum machine a certain state. This could be an approximate ground state of a system. It could be a thermal state that you have over here. Quite amazingly, you can do the inverse, and you can try by measurements on the system, and we can do these measurements on the system to learn the structure of the Hamiltonian back, so we can infer from a prepared quantum state what is the underlying Hamiltonian, that gave rise to this quantum state. So what is the Hamiltonian of our synthetic quantum matter that somebody prepared over here? This technique of learning the Hamiltonian back rather than implementing the Hamiltonian and creating the quantum state, we go in the other way, so it's really inverse, is exactly what this so-called Hamiltonian learning does. So we're learning the structure of a Hamiltonian, of a synthetic quantum matter back in our quantum device. So why is this useful? Well, one way is useful right away, and this is a way of verifying that your simulator actually implemented the right Hamiltonian. So it becomes a verification story. Studying fundamental physics, in an obvious way, but new direction. This is the one I just want to point out briefly. Is the so-called inverse design here. And what do I mean now by inverse design? Well, let me first just point out that what Hamiltonian learning is, because it's quite remarkable. This is now, I would say, one of the hot topics that we are facing in quantum simulation. Suppose that you get a many-body system over here, and of course it will be governed in your synthetic quantum matter, or also real quantum matter, by some Hamiltonian age. And these are the energy eigenstates that you might draw. And what this Hamiltonian learning says, for example, is this: if you prepare one of these eigenstates, then it is possible to reconstruct the corresponding Hamiltonian. This seems, at first sight, something which doesn't sound to be true, because we have a counter-example over here. If I take a Hamiltonian like this, I could multiply. This would be eigenstate. I could multiply it by an alpha, so it's not unique. Counter-example would be I'm writing down projectors of the eigenstate. If you allow me to put my head on the theories for the moment, also doesn't work. The whole story behind it actually is like this, that it works, and all of these papers discuss these kind of things over here, that if you require that the physical Hamiltonians of real materials, and this is what we do in quantum Hamiltonians, are local Hamiltonian, that you only have one body, two body, three body term that act in the local environment, it turns out that this reconstruction is here unique. So amazingly, if you prepare a quantum state and you say that the underlying Hamiltonian is quasi-local, there are mechanisms of allowing you to do all of that, and we know how to do it in practice. So if I illustrate this with an example, when we do, for example, here a Hamiltonian that would correspond to a Hubbard model in 2D. These are fermions, and we know how to do these things in our quantum simulations over here. We can, solve, in this sense, a classically hard problem, and we would then get maybe a phase diagram showing superconductivity, like D-wave superconductivity, one of these things that theoretically we don't know how to calculate yet accurately. There's a lot of calculations out there, but we can simulate that. That's what sort of quantum simulation does at the moment. But now, suppose that you can ask, how do I have to change my Hamiltonian over here, that I increase my superconducting dome, so this phase that I'm looking for, I would like to make it larger, maybe even more high temperature. If you read these papers, they give certain hints about it, but we can now use a quantum machine to do that, because we can write down a list of properties that we want, a wish list of material properties. We can encode this wish list of material properties into a cost function that we solve on our quantum device, like Fermi-Hubbard models as a programmable quantum simulator, leading at the end to the Hamiltonian via Hamiltonian learning. So it really goes here that you write down a wish list, a quantum simulator solves for you the problem of optimizing, the phase that you want to see, the features you want to see. This could be conductivity, susceptibilities, all of these things. And then you're learning the Hamiltonian back that corresponds to the situation that would actually realize the material. If you learn the Hamiltonian back, maybe a chemist could synthesize the corresponding material that according to that would have the wishlist properties that you would have over here. So we're just writing a paper about this at the moment, now to be submitted very soon, but I guess you sort of get the idea, and I could go now through all of these things of technical details, how we optimize, D-Wave over here, how we program our device and find, for example, what kind of, how the machine tells us to add certain terms like cross terms over here, the tunneling and so on. And these seams on a piece of paper work very well. We would like to see this in a real quantum machine. This would be an example where a quantum simulator would solve a highly relevant problem, quantum material design. Of course, here only on the level of toy models, but I think in a very new and conceptual way. Okay, so I'm now basically at the end of my talk here. I just want to have now 2 more slides and point out one topic that I'm also very intrigued in at the moment, which is the fundamental question. We're building now quantum simulators or quantum computers in a regime of quantum advantage where we know that we can no longer classically simulate. How can we trust these quantum simulators as devices solving a many-body problem, making predictions with certified accuracy in the regime of quantum advantage? And we've developed some theoretical concepts along these lines, and we have implemented them actually already in first experiments, again, sort of demonstration experiments. And to simply explain it in a sort of most simple way, what we do is this, that you say that, well, to the experimentalists, give us your quantum device and we treat it as a black box, but we would like to learn back the Hamiltonian, that was realized in the black box over here, just only for measurement. There will be learning errors over here, but if you use this quantum device here for computations, we will predict observables over here, and knowing the learning errors over here, we can also compute the error over here. So in other words, we are on the way of teaching or doing with our quantum simulators now real experiments, or sort of we are devising the theoretical concept, where the quantum simulator not only gives you predictions for the observable, but it also tells you the particular experimental machine that you had, we know the Hamiltonian have learned it with a certain error, how this error propagates at the end to the observable. So we are doing bounded error quantum simulation. The machine gives the values, but also assigns an error bar to it. And this can be done on analog machines and so on. And I'll just show you some results along these lines without explaining the details. So we know how to do this. So the quantum machine computes observables and also error bounds over here. These are completely new results. We're just writing out the paper. Okay, so let me now conclude my talk over here and sort of come back. One of the slides at the very beginning was that we said, the quantum computing community came to us and said, how to build a quantum computer simulator with AMO. And I think that 30 years ago, 20 years ago, there was a lot of theoretical proposals. They have become reality in the meantime today. Quite amazingly, these scribblings that were on some blackboards are now reality, and now they're coming back to us to use. The holy grail being this quantum advantage and quantum computing, of course, fault-tolerant machines. And I think that we are at the threshold right now where we can now really do highly non-trivial things, and this is really the result of a long-term development where we as theorists are able to make contributions, experimentalists made these fantastic experiments, but I think that we are now progressing from this quantum science to a quantum technology. But a lot of the basic quantum science, of course, is not yet solved, but I think it looks pretty good. Thank you very much.
Thank you for the great talk. Now, time for questions. The floor is open for questions. Please come to the mic. Questions.
Thank you for the nice presentation by Professor Zoller. So I have a question on the Hamiltonian learning part you introduced to us. So actually I was doing a similar thing in my previous research, and I recognize that not only the Hamiltonian itself, but also the open system quality of the experimental system. For example, the Lindbladian parameters are also important in the system. So do they play much significant role in the Hamiltonian, or is it sufficient to just identify the Hamiltonian itself?
You're completely right. We also wrote papers about Lindbladian learning and other sides. So in the experiment that I just mentioned on the previous slide over here, in this experiment we are learning both the Hamiltonian as well as the Lindbladian, in this case over here. And we can identify what the decoherent structure is in the quantum device. And all of these things are included in our analysis. I just simplified the discussion here to Hamiltonian, not to overload the audience now with Lindbladian open quantum system, all of that, but you're completely correct that this has to be done to include the decoherence model, if the Lindbladian is appropriate way of describing it, and we are learning in these experiments the structure, the quantum jump operators, the structure of Lindbladians that exist in experiments, and we quantify them. And some of these experiments were done with 10 ions, but they work in the meantime now also with 51 ions. So we can really do large-scale learning in these systems here. I should mention that LUMIC 1 has for 500 ions done some Hamiltonian learning. It's a very, very simple system. We are doing high-precision learning of Lindbladians and Hamiltonians with this 51 ion system here at the moment. Thank you for your question.
Thank you.
Okay. Any other question?
Hello. I have a question about the cost function that Hamiltonian learning. How do you know that the cost function after optimization do not end up with the Hamiltonian that isn't local?
Okay. So Hamiltonian learning sort of makes the assumption I give you a many-body state, and I can learn Hamiltonian that would correspond to a quench dynamic, could also be a stationary state like being the ground state and so on. And of course, in general, if I write down a single quantum state, the Hamiltonian, if you don't make any assumptions or constraints, will not be unique. So otherwise, I could just write down the projector plus something else, and then something else can be whatever. But it is the locality of physical Hamiltonians, many-body Hamiltonians that we have in an engineered many-body system. There will be 2-body interactions, 3-body interactions maybe, but there will not be 100-body interactions. So this means that the number of parameters that you have to learn in the Hamiltonian scales polynomially with the system size. And this allows you to do at the end Hamiltonian learning in a regime of quantum advantage, where the Hilbert space goes exponential, but your Hamiltonian only has a polynomial number of parameters, scaling with the system size. And this allows you to do that. So that's an assumption that you make, that it must be sparse Hamiltonian. Many papers out there describing all of these things. This is working now in the experiment. If it's not true, then the flag goes up in the way how we do it and tells us we are not able to learn the Hamiltonian because it is a random Hamiltonian, whatever, and then these things don't work, but then we know that it doesn't work. Okay, so the red flag goes up, and there's many regimes. But for physical many-body Hamiltonians that are constrained to be 1-body, 2-body, 3-body, and so on, a small number, this is a very viable way of doing it, and we're doing it now continually.
Thank you.
We can take one more question. Okay, I have one last question. So, you have shared the fundamental studies or academic demonstration of quantum simulators. So, I guess that many are curious that when we can really achieve the practical quantum advantages based on quantum simulation.
So I would say in terms of the numbers that we have at the moment, you saw that the Aquila regime had 256 qubits. It's in principle, if you do very non-equilibrium dynamics, very far away from what you can simulate classically with DMRG or whatever your techniques are. It doesn't mean that in a particular problem that you study you always have this large entanglement possible, but in principle, this is the case. So I would say that these machines operate at the moment in the regime of quantum advantage already. We have the question of can we trust them or not and all of that. But I think the important point is people always say, well, quantum advantage, what do we do? I think it's important to say at the end what we like to do is with our quantum simulator, quantum computer, solve problems that have utility, that are relevant problems. Okay? So we don't want to reach quantum advantage by itself. Well, Google has shown that, of course. But we also would like to solve relevant problems that people are willing to pay money for. This is what we get money as a community when we do quantum science and technology. And so we would like to solve relevant problems, where the quantum advantage will play an important role. So I always would like to include the word utility in this sentence. Let's solve problems with quantum advantage that people care about and are at the end maybe willing to pay money for.
Thank you. Let's thank the speaker again.
일단